yes, it's not like I've ever done anything like that before. Never, I don't make those jokes ever. Oh no, God, what even is being edgy? What even is wanting to die?
Why you gotta be so edgy?
Because the best kinds of jokes are the ones that are true. I'm gonna be really mad if I'm not better by the end of the day. I'm ready to die.
You win. And it matched the beat. What homework is this? Homework 12?
Okay, number 1 is time-like. Number 2, if you put it in SI units, then it would be 3.3 times 10 to the negative 8 seconds. Number 3 would be either 9 times 10 to the negative 4 light seconds, or per meters, it would be about 270,000 meters. Number 4 is no. Number 5 is B. Number 6 is E. Number 7 is negative 2.93 meters squared. The units of the space-time interval should be meters squared. Number 8 is 0. Number 9 is 0.148 square meters. Number 10 is A. And the challenge is root 5 seconds. The challenge is actually not that hard. I told you how to do it. Anyway, I hadn't told you about it. Okay. Questions? Sir? 9. Number 9 is space-time interval between Jimbo entering the barn and Jimbo finding out what happens to the pole. Didn't we do this one?
Yeah.
Didn't we do this one like in class?
Mm-hmm.
Does it come out to the same answer?
Mm-hmm.
Okay. It should be, do you remember your factoring the C and stuff? It should be the time coordinate, if him entering is 0, 0, 0, 0, the time coordinate should be, what was it, 4 over root 15 plus 2 M over C. That's what I wrote on the board yesterday, wasn't it? Remember, right? So the 4 over root 15 is the amount of, this is right? The 4 over root 15 is the amount of time it takes for the pole to hit the barn. And then the 2 is the amount of time it takes for the pole having hit the barn to the explosion or whatever the thing goes at the speed of light back to reach the front of the barn. Yeah.
The guy still, but he doesn't stop.
Oh, does he not stop in this example? Oh, okay, that would change things. Does it change the answer? Oh, is this what I mean, is that, I haven't worked it out numerically, is that what I said? What did I say the answer was? 0.148. Doesn't seem like it would come out to 0.148. So maybe that's the issue. So if he's not stopping in this case, then I didn't realize that. Sorry. Then if you have the barn, right? He is right here. Then he continues. Okay. The pole also continues, right? So that means when the pole hits the end of the barn, where's Jimbo?
Inside the barn.
He'd be right in the middle of the barn because the pole is 1 meter long, right? This has already taken 4 over root 15 M over C, right? Yeah. That we already factored, right? It's just distance, not value velocity. Okay. Then from then, he keeps going this way. The light will come back this way. So he's going at root 15 over 4C. The light is going at C, right? You can you can do a quick way is to say, okay, the relative speed between them, by which I mean the speed at which the distance between them is decreasing, is dropping it by a factor of root 15 over 4 plus 1 c. Of course, that number is greater than c, but in this case, it's not the velocity of an object, it's how quickly that distance is decreasing. So, therefore, you can find the time to be the distance 1 meter divided by this thing, root 15 over 4 plus 1 c. And at this point, you would want a calculator. The position that he ends up with, where it reaches him, somewhere over here, that position will be equal to the time times his velocity, root 15 over 4 plus 1. We started at position 1. That would be his x-coordinate. This is all algebra, right? There was no changing in reference frame. You could choose your own reference frame. This one seems like one convenient one, although actually maybe I wonder if the other one would have been easier. I watched it when Joe gets inside, yeah, it was about the same. Yeah, so maybe the other one would have been easier, doesn't matter. You can do it in either reference frame, you'll get the same answer. So you have an x-coordinate, you have a time coordinate, you'll want your calculator to, simplify those. And then you just take t squared minus x squared, Vector space-time interval. Yeah. Number 4, why is it no? Because the student claims that there is some reference frame in which the two would be simultaneous, right? Two but being simultaneous means the time coordinates of both are the same. Since we choose one as the origin, that means the time coordinate would be 0, right? But the rule we found with light-like intervals is that t and x can never be 0. Neither of them will be 0. They're always equal to each other, right? They would never be 0 because that would make those two the same event. So if they're separated by anything at all, they would never be 0. And therefore, there still is no reference frame in which they're both simultaneous. The light-like interval is uninteresting because instead of being like both time-like and space-like, it's kind of neither time-like nor space-like, so like nothing interesting happens. So that's why you cannot make a causal relationship because the time can never be equal to 0. Sorry, you could have time can never be equal to 0, that's not what I meant. Time can never be equal to 0, therefore they will never be simultaneous. Basically, it's right at the limiting case. For that to be simultaneous, the reference frame would have to go the speed of light, but we don't know how. Yeah.
Limits on 2 and 3, then wouldn't that make it a right?
Would that make it? Yeah, the limit is the light-like limit, yeah. Because basically, the light-like is the limiting point, right? It's really a kind of an open interval there. So if you're just past that limit, that doesn't work. So that's a good point. But that's sort of like, so technically the minimum value is that plus epsilon or whatever, right? It's just past that point, like an open interval in that. Good question. Sure. For 2 and 3, the question is, so here's the thing. What we discovered is that s squared is greater than 0, right? That is to say, c squared t squared minus x squared is some number that's greater than 0. So the question is, the first one is about time, right? The question is, what time could it be? What time would work so that s squared would be less than 0? That's really what's asking. It says, for its argument to hold, it has to be a space-like interval, because that would allow you to change orders in different reference frames, right? So for its argument to work, you would need, you would want s squared is less than 0 to be true. And that's the only way its argument can work, because then, if it's space-like, then you can have a frame where they're simultaneous. That is to say, you want c squared t squared minus x squared to be less than 0, which means c squared t squared has to be less than x squared. Given that for a fixed value x squared, you can choose a t, then you can choose what's the value of t, and like Emily pointed out, it's slightly less than the value I quoted, right? Anything less than the value I quoted would allow the interval to be space-like. For number 3, it's the same thing, but reverse. You keep the value of t and fill in the value of x, that will make this true. So basically, it will work only if the time between them is absurdly, absurdly small, or the distance between them is absurdly, absurdly large. Right? So if the teacher taught in a class group that was the size of the Milky Way galaxy, then the student would have a point. Because coming in the door would be so far away from the teacher that you actually could look at a different reference range. Or if the teacher is an extremely sensitive clock, instead of marking a few milliseconds late, marked him a few, it wasn't him, right? Did I say him? Or did I just say the student? Anyway, mark the student a few picoseconds late, then again, that would be sufficient for the student to make this argument. Right? But because there's this factor C squared in there, it only works when you have things that are like in that the kind of the order of C squared, right? It is what makes things work. So the math of it is nothing complicated, right? It's just understanding how the interval works. Yeah.
Okay, so do you include the C squared if it's not included?
The reason you need to include C if your answer is, you usually need to include C if you have an answer in meters or seconds, or in SI units. The one exception is light seconds. If everything's in light seconds, it works if C equals 1, because that's such a nice unit to work with. But if you want sort of like real life answers in meters and the normal things, then you've got to use the C in there. In particular, C is a length over time, and so if you want answers that are lengths and times, you kind of have to have the C's in there. All the same, you can stick the C's in at the very end still, which is totally what everyone does. Because you still want to save yourself the trouble of writing them the whole time and making sure they cancel and stuff like that. Like, do you remember that one problem at the end of the quiz, the level 3 on our first quiz, was the one with the speed of light and the one where it's traveling? It takes the proper time is 1 year, but the proper length is also 1 year, and sorry, the proper time is 1 light year, the proper distance is 1 year, and I mean proper time is 1 year, and the proper distance is 1 light year. Yes. And and a good number of people got the idea of how to work it out, but got bogged down with the factors of C, right? So that one, you definitely just let C equal 1 becomes a much easier problem, and then stick the C back in where you need it. Yeah?
Will the space-time interval be on the quiz?
The space-time interval will not be on the redemption quiz, it will be on the exam. I consider it too small a topic to bother with its own section of the quiz. Okay. Good. Any more questions? All right. Well, that's our last homework of the unit. I should post a review sheet. If I don't do it, remind me. Okay. I'm in real forgetful since I have pulled this on the floor. So please, yeah. If I don't have it up there, remind me. Like I'll try to remember. But it's important, so it's not up. Then you should remind me. What I do for the review sheet, I post a like 2-pager that goes over everything you should know, and I have a many more than 2-pager that is basically all your homework problems with different numbers re-rolled up into a big Okay, so that is not everything. That will not give you everything for the test, but it's a good review. Okay, I recommend don't do them all. I mean, you can. Some people do it. Okay, but like I would rather you prioritize. It's probably going to be 100 problems. Probably prioritize which ones are worth looking at. So I recommend you let me practice this, so I need to remember how to do this. Oh, I know how to do this one. And I recommend using a little triage here. Yeah.
So like to go like above when you're studying, what would you recommend?
For the quiz, I don't think you need to worry about too much. Okay. For the exam, I'll talk more about it later, but if you're very comfortable with having homework, probably the best thing to do is to try and figure out what kind of question Dr. Don might ask you to screw everything up. And then, probably the best thing to do is to write questions for each other. Find get a group and write questions to put it on a Facebook group, whatever you want. But I mean, that's probably the next best preparation after that. Yeah.
Are there going to be any acceleration problems on the test?
Not explicitly. Obviously, accelerator has a lot to do with energy momentum, so you should still know that, but nothing explicitly. You do not memorize anything.
Particle acceleration.
Yeah. No, do not memorize anything. Oh, about acceleration.
Okay.
That's not special. That's general. I mean, yeah.
Well, yeah.
Yeah. So no, absolutely not.
You can do a special with energy.
And also nothing from the project explicitly. Do not memorize anything about particle accelerators specifically. You still need to know Eastern ice cream pretty close. But you don't need to know synchronous radiation. That's an idea, but not to worry about that. You have not to worry about it. Let's keep it focused. Okay. All right. Speaking of focus, I really want to talk about stuff today. I love this material. So here's how today's working. There's no homework on it. It's all very conceptual. And I will put one question on the exam about it. Okay? All right, there you go. So remember last time we started it? What did we start? What did we talk about? General relativity. What was the theory of general relativity?
Laws of physics are the same in every reference.
Good. The laws of physics are the same in every reference frame. Technically, that's not entirely the theory. General relativity is a lot harder to work out than special. And so Einstein actually had to make a few more sort of mathematical assumptions. The laws of physics are second order in the Riemann tensor and things like that. So you don't need to worry about that. But he did actually have to make a few extra assumptions, which he didn't do in special relativity. But remember, here's the thing. The laws of physics are the same in every reference frame. What makes a reference frame inertial? How do you know you're in an inertial reference frame? No what? Good, no fictitious, we call them fictitious forces. No fictitious forces, right? If you're not in an inertial reference frame, what laws are not true? Newton's laws are not true in a non-inertial reference frame because you get those extra acceleration things. Okay, that means that the laws of physics are the same in every reference frame, then Newton's laws are not laws of physics. Now, this is not any kind of attack on Newton's. Newton's laws are awesome. They're never wrong as such, but they have a limited application. They only apply in inertial reference frames. And if Einstein needs to write something that will work in any reference frame, he cannot use Newton's laws. Okay? Makes it rough. Einstein thinks very, very hard about this and comes up with some really interesting stuff. He thinks about acceleration and comes up with an utterly fascinating and apparently, as far as we can tell, completely true issue. Anyone have SI physics with me? It's been a while. All right. The religious era? Wow. That's right, because I didn't teach it last year. Okay. All of you are teachers. Okay. Well, I'm not teaching it this year either. Huh? Okay. Well, you've covered it. SI physics covered. I mentioned it when I teach it. I mentioned it. SI physics contains one of the weirdest facts about nature. Okay. It's in the free fall unit. What's that?
Is it like inertial? There's two types of inertia, and they both.
There are two types of mass. There's this weird thing that you have F equals MA, right? You remember this one, right? This is called inertial mass. And remember, its mass is defined as resistance to acceleration, right? It tells you if you put a force to it, how much does it move? Any force, right? In fact, usually a combination of forces, right? And the net force here applies to it, and the mass tells you how much will it move, right? The mass here is completely independent of which force you're applying. It's the property of the object itself. Okay, and then you have another law. Please tell me you know this one.
Yes.
Gravitation, good. Law of universal gravitation, right? And this one has this mass, which we can call gravitational mass. Here, gravitational mass just tells you how strong the force of gravity will be, right? If the mass is larger, the force of gravity will be stronger. If it's smaller, the force of gravity will be weaker. That's it, right? It is gravitation specific, and it's only about gravity, right? It just tells you how strong the force is. But this is the part that tells you that applies to any force and applies to the general motion of the particle. And this is the part that's only about gravity, very specific. And yet somehow these two ends are the same quantity. And that is the weirdest thing about Newtonian physics. And Einstein sets out to find out why. Okay? And he comes up with this. Gravity, he says, is special. Okay? There's a lot of forces in the world. Gravity behaves differently from the other ones because it's the only one that is dependent on mass. Why would gravity be dependent on mass, which is an inertial property, right? All the other forces depend on other things. Electrical force depends on charge. Magnetic force also depends on charge and velocity, right? Normal force depends on a whole bunch of other things. Friction force depends on the normal force, blah, 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 right? There's all these other things that depend on. Only gravity depends on mass. Only gravity. And he said, gravity is special. I think gravity is not like the other forces. Okay, it's not just something that can be described like this. And he comes up with the brilliant idea of, by the way, this has been tested experimentally to an absurd precision. So it's true, those masses are the same. He comes up with the equivalence principle. And the equivalence principle is that gravity and acceleration, that's combined. This is gravity, this is acceleration, right? This gravity and acceleration are the same thing.
What?
Here's his argument. Let's imagine you're standing in a house without windows on the earth. Any question? And then you take a ball and you throw it at the wall. Okay, because you're on the Earth, the ball does not go in a perfectly straight line towards the wall. What happens? Gravity makes it curve down and fall like that, right? Good. Now imagine you are in the same sealed room, okay, so you have no windows either way, so it's basically instant. And you are in outer space, and the rocket ship is accelerating this way at 9.8 meters per second squared.
Oh, hey.
So what's going to happen? You stand here, you throw the rock against the wall. Once the rock leaves your hand, it is no longer you, when you're standing on the ground, are being pushed up constantly by that acceleration, right? But once the rock leaves your hand, it is not being pushed up by the acceleration, which means as it flies, what will happen? The floor will start to accelerate towards it, right? Because the floor accelerates, it does not. Therefore, what will you see happen? The rock will curve down as the whole spaceship accelerates up. Look at the little map here, you discover these are exactly identical in every way. Einstein extends this a bit and says there is no way to tell the difference between these two things. Thus, gravity and acceleration are actually both the same thing.
Whoa.
Right?
Why?
Because. Yeah. If you can't tell the difference between them, then they're the same thing. That's the error. Yeah.
Well, like, I guess, I don't know if it's a dumb question, but like for forces that are not going like strictly down, so like something that's like...
Well, it's not gravity. Gravity points down, you know that one, right?
Yeah,
Okay.
so then it would just be an acceleration caused by a different force, right?
Basically, it says gravitation is a manifestation of acceleration. Let me walk through it a little bit to see where it gets this from, okay? I'll hold off on this a little bit. But first, look at this interesting conclusion from the equivalence principle. Let's take the same rocket in outer space. You have a guy here, now instead you have a flashlight. Now, you shoot a beam of light and go straight, right? But as the light flies, what will happen? Just for the exact same reason as I gave before, the floor is going to accelerate up towards it, right? Meaning, what will you see happen? It'll kind of bend down, right? You'll see as though the light were aiming down here. If the equivalence principle is true, then if you're in a house on the Earth and you shine a flashlight, if the equivalence principle is true, then you will see the same thing happen here, which would mean light is affected by gravity. But light has no mass, you're right. But Einstein's equivalence principle predicts that light nonetheless will be affected by gravity. This is now a testable prediction. Right?
Why the light moves down in the spaceship?
Do you understand what the rock does?
Yeah, because the floor is accelerating light.
Okay. Well, this is just a fast rock. The floor does the same thing either way, right? This is about the motion of the floor, not the motion of the rock, right?
The person who's like shooting the light is also accelerating.
Right, exactly. So you and the light are all moving up, right?
Yeah.
But then you keep accelerating, right? While the light's in midair, it is not being accelerated anymore. You can't accelerate light, right? And so then the floor accelerates towards it for the same reason. It is all about acceleration. It doesn't work without acceleration. Okay. So, interesting. Okay, let's leave that for the moment.
Okay, hold it. No, you can't do that.
No, because to get back to it, we need to talk a little bit more about the math of relativity. So Einstein came up with this example. I really like it. Let's talk about a rotating reference frame. Okay. Yeah. Well, let's see. Of all the accelerating reference frames, rotation is probably the simplest one, right? Let's take a reference frame that's rotating at a constant velocity, or constant, rotational velocity, right? That's probably the easiest reference frame you can think of. That's not inertial, right? So let's take a simple object that works well in a rotating reference frame. A circle. Yeah. Okay. So here's a circle in its own rest frame. So let's suppose I want to measure the diameter of the circle. What do I do?
Where are you? You take a tape ruler and you go around.
Diameter.
Oh, diameter. Just go.
Okay, good. You take a ruler, you go across. What is a ruler really? Seriously though. What is a ruler or a tape measure or any of those devices? What are they really?
A construct.
Social construct.
Yeah, I know, social construct, right? But like, yes, the patriarchy, all that I got. Well, what is it really? Seriously.
A piece of wood.
It's an object. Why does it work as a ruler? What is a ruler fundamentally? What that makes it work? It's not a representation of a distance. What is that makes a ruler work?
People say it's a standard length.
Yeah. But you're right. I understand the social aspects of it, and the oppressive aspects of it. I understand. But what makes a ruler work is that everything that's marked as a centimeter is the same, right? The key part is the same. So really, what any kind of ruling device is a series of identical things laid end to end.
Wait, what happens when it undergoes?
Let's hang on. I'll think of it.
Okay.
Does that mean a line of identity?
No. But even then, the whole ruler undergoes length contraction. You're still fine, right?
Okay.
But a ruler is really a series of intervals of distance that are all the same, right? So you can imagine a ruler as being a bunch of sticks that you're laying end to end. It's not, of course, but it's fundamentally the same thing, right? So imagine a bunch of little things that you lay end to end across it. You count them up. That's your distance.
Okay.
Agreed? That's how we actually measure distance. Good. Now, let's measure the circumference. How do I measure the circumference? Measure, not calculate. Good. You take a string or a tape measure, something flexible, you run it around the edge, right, and then you measure it. So basically what we're doing is the same thing. We're taking a bunch of these things and we're running them around the edge. As long as the little intervals are very small, this is a calculus argument, right? As long as those intervals are very small, you can imagine it as just, that's what a tape measure is basically, right? It's just a bunch of very small intervals laid end to end around this, right? And then when you're done, you count up how many you have. That's the number of millimeters you have or whatever, right? Good. So that's how we measure circumference. So, if you take the circumference and divide it by the diameter, what do you get? Pi. Good. Then you should have. Okay, good. Now let us switch into a rotating reference frame. So it's the same object now viewed in a rotating reference frame. So now it's rotating. It looks about the same. It's a circle. Okay, now let us consider the guys that lie around the edge. All they are you can imagine them as little tiny sticks that you're laying end to end. It's not really what you're doing, but you can think of them that way, right? If you are laying these little sticks end to end, then what is going to happen when it's rotating now? What's going to happen to those sticks?
The sticks are going to move round and round.
And what happens while they move? They're going to length contract.
Does that make the sphere smaller?
No, because you can actually make, because the sticks, the circle is still a circle, right? But the sticks are shorter.
Well, whatever, because the sphere's spinning, it's going to be applied to the surface of the Earth as well. The length contraction.
It's not the Earth.
Or whatever, the big ball of goo.
Yeah, you say the length is prime curve, but it's a circle, no matter what.
Circle.
So how do you length contract a circle?
But it'll be the outer edge of the circle.
Well, what I'm doing is I'm telling you how to length contract a circle. You take, if you wanted to measure the length of the circle, right? Now if you try to do that same measurement, your sticks are shorter. As a result, right, your little marks are shorter, which means, how many can you fit more of them around now? You can fit more of them around now, right? So the circumference increases. C is circumference, right? The circumference increases. Now consider your diameter. Now, which way is the circle turning? I mean, it rotates like this, right? So, what effect does length contraction have on the measurement this way? Right, it should make the sticks thinner, right? But not affect their length.
But when it gets to the middle of it, it's going to make it...
No, the motion is all perpendicular to the sticks. So the length of the stick itself will not be changed. They're going to squish this way, right? But it won't affect how many sticks there are this way. Meaning that the diameter stays the same. Which means circumference divided by the diameter is not pi. Yeah.
When you're putting the things around and contracting, wouldn't the circle length contract as well?
I mean,
Like, the area, the circumference of the circle is smaller.
the circle shrinks.
Yes,
We don't have that. We don't have that.
but.
The diameter stays the same. Remember? It just showed the diameter stays the same.
But how can like the object right next to the edge of the circle shrink, the edge of the circle doesn't also shrink?
Well,
They're both moving the same speed.
what we're saying is that the circumference is increasing, right?
Yeah.
For the same reason. Because it's still a circle, right? It remains a circle, but you need more sticks to go around it, so the circumference has increased.
Well, if I have like an object with a circle,
Yes.
and I put, I guess, a circle of tape measure around it, how come my tape measure shrinks when the circle doesn't?
The circle does. The tape measure is not shrinking
Okay,
like this.
contracting.
It's each individual, it's contracting only around the circumference, right? It's the same circle. What do you think, Chris?
I'm just confused about like if the sticks are like meant to be captured, when the stuff between the sticks are like to be captured.
What do you mean by the stuff between the
Like
sticks?
whatever space between.
Yeah, well, no, you're laying the sticks end to end, so there's no space between them. So that's how you make the measurement. You just lay sticks and you count how many you have, right? Millimeter long sticks or whatever.
Okay, how does the
Hang on. Wow, okay, let's see. You count all.
Wait, so what you're saying is that the space it's measuring doesn't change, but the space that more sticks will be measured the same space.
I don't think that's quite the right way to think about it. I would say it is you are measuring a circle, but we have to define what measuring means, and we've defined what measuring means. And if that's what measuring means, which is the only sensible definition, if that's what measuring means, then the circumference, if it's rotating, the circumference has to be changed. Now,
Okay, so like these little sticks, right, they're getting shorter, but then wouldn't that mean that the, like, part of the circumference that they're attached to, wouldn't that have to get like...
so like what, a hole opens up in the circle?
No, it just like kind of...
Shrinks, that's diameter, not circumference.
Okay, well then my other question is, so if these little sticks like shrink, and then you add more sticks, but the sticks are now smaller, so then how do you know that there's more smaller sticks is greater than
Because
the...
it's still a circle.
But,
It's got the same diameter. So therefore you're going to need more of them to get around it.
I don't like this anymore.
No, this is,
What an interesting question. What do you think about that? Go ahead.
So I'm also confused why the circumference increases because the sticks are smaller, so then the units of the measurement are also smaller, right?
The measurement is the number of sticks it takes to get around.
But like, if we were using something like a tape measure with like actual units on it, the lines on the tape measure would get closer together. That way, like there would be like less lines, I guess. But that means like if you compare it with a real tape measure, then one tape measure would have smaller lines and one would have like normal ones. So then wouldn't the circumference just stay the same?
No. The tape measure, we measure this thing by, this thing is now a rotating object, right? You're trying to measure a rotating object. So you measure it by putting sticks on it, right? The sticks obviously have to be attached to the object or else it's not going to work, right? Therefore, the sticks are going to be rotating too, and therefore they're going to be shorter because they're moving.
Yeah.
And therefore you need more of them. When you try and stick them on to the thing, you're going to need more of them to get around. So when you measure the circumference, you're going to have to count up more of them.
The sticks would like be smaller though, and then there's
The sticks width and length. Yes, so you need more of them.
Yeah, but like the sticks like in like normal sticks would be bigger than those like.
Normal sticks are still the same size, but they're attached to, for it to work, you have to attach them to the circle that's rotating, so they'll be shorter. Micah?
I want to know, I actually have two questions. I want to know how the measurement shrinks, but not the object itself. How the measurement undergoes lens transformation, but not the object itself.
Okay. So, the object does change.
Okay.
What we are doing is quantifying how the object changes. I will tell you how the object changes. Its circumference increases, but its diameter remains the same. That is how the object changes.
Okay.
Jane?
So you put the tick marks on the circumference of the circle itself while it's not rotating, and then you rotate the circle.
Then, of course, but that will only tell you the measurement in the circle, in the object's rest frame, not the measurement in a rotating rest frame, in a rotating frame. Is there a question? Okay. All right, go ahead, Micah.
My second question is in a sphere's term, the circumference would be different because one would be rotating this way and it would affect Lorentz transformation, but the circumference this way is rotating this, the circumference this way.
The sphere, I mean,
It
rotation
would
only
turn
happens around
kind
one
of into
axis
like
at
an
a time.
oval shape or whatever.
Yeah, it
Rotation
would
only happens
kind of
on
like
axis
the one,
at a time,
the
so
one
it's
would
not-
get bigger.
I see what you're saying,
And then it would
but
stay like the same.
the basic idea is still applied here. All right, Emily?
So for the area, it would get bigger because it's no longer measured in like the square even because one section of the square would get bigger while the other one stays the same.
I'm gonna let you work on that. Okay.
This problem has been left.
Okay, all right, a few more and then we're just gonna move on. John?
Question. So if we have the tick marks on the surface of the circle, and these are equivalent to our like stick units, like they're the same size, and we start spinning the circle, the tick marks should contract close to each other, right?
No, the tick marks are off in the circle surface rest frame. The problem comes when we try to, and when we see the circle spinning and we try to add our own tick marks to it. See, that's the difference. If you put the tick marks on it and then spin it, those are only measuring the circumference in the circle's rest frame. But if the circle is spinning and you put tick marks on it as it spins, right, then you will end up with more tick marks.
So, but like, what if we
Don't try to visualize it. You can't.
What are we supposed to do then?
Just take it for granted.
Only Dr. Dong can. Dr. Dong is God.
It would no longer be okay, put sticks on the circle.
Sorry, just don't trust like that.
Right.
Space won't open up, let's put more sticks.
Right, of course not, because then you'd only be measuring it in its rest frame.
Okay, that makes a lot of sense.
No space opens up anywhere. In fact, that's the whole problem. No space opens up anywhere, but lane contraction still has to happen. That's where all the problem is. That's
What? I don't.
It's because you guys have been asking so many questions. It's
because the motion, when you're doing circular
He's been like,
motion,
okay, I'm gonna go do that, and you're like, well, that
all the
doesn't
forces
work.
called velocity, that means you velocity goes this way. So along the circumference.
Okay,
tangential,
I still don't understand how the tick marks undergo, but the sphere itself doesn't.
The motion is perpendicular.
Like, it's getting larger.
Thinner,
Lorentz
but one
transformation
change
should make the surfaces
It's
here
like
smaller.
in the direction of motion. So it only affects the circumference once, not the diameter.
Yeah, it should.
Okay, I'm gonna need to move on.
But-
Not that means you understand everything.
No.
I appreciate that, but we're going to move on. No, we're going to move on. So, some people that can't hear well. Okay, so, if you're trying to visualize it, you will fail. Okay? This cannot be visualized, because we do not have circles that do this. Right? Circumference divided by diameter cannot not be pi in our normal behavior of things. And so, by the way, the result of this is Einstein concludes that
I swear, if it's like this doesn't happen.
But he's just a monster.
the geometry is relative.
No.
That's it. All right.
Yeah.
So, what does that mean? It means that laws of geometry, certain laws of geometry,
Someone get
change
Porzio.
in different reference frames. Yes.
I have a question. It doesn't have anything to do with like the circle necessarily, but like when Einstein just comes up with this thing and he's like, "Wow, this doesn't really work," does he just say it's relative and move on?
No, Einstein never moves on. He attacks it, right?
Well, he tries to, and then he.
So, let me talk about what he does next.
I thought you said all laws were.
Literally everything he would.
Yeah, so obviously some of these things are not laws. In particular, you know the one that's not is it's Euclid's fifth postulate, the parallel postulate. Through a point outside a line, exactly one line can be drawn. One parallel line can be drawn. That's Euclid's fifth postulate, the parallel postulate. That's the one Euclid tried to prove that from the other four. He couldn't. It turns out to not be possible. So he had to add a fifth postulate that he really didn't want to, called the parallel postulate. Through a point outside a line. You know Euclid's law. You know who Euclid is. He invented geometry, right? He invented two-column proofs. You have him today. He thought he could do it all with four postulates only, and he had to add this fifth one, which is through a point outside a line, exactly one line parallel to that line can be drawn. That is the one that gets thrown out here. Okay? Fortunately, Einstein did not have to do all this work himself. A lot of mathematicians had worked on what's called non-Euclidean geometry, where circumference divided by diameter is not always equal pi. In fact, you can even visualize it. Here, let me show you. You can visualize it if you're careful. Let me show you an example. Here's a hill. Here's a circle.
Okay.
Now look, if you measure the circumference of the circle, and you measure the diameter of the circle with a tape measure, and you divide those two, you won't get pi. You measure the diameter like this.
Why would you measure the diameter like that?
Can you burrow through mountains?
Yes.
Wow. Okay. Right, so you measure by your, well, here's another one then. This is the Earth. Here's the North Pole, here's the equator. Beautiful, right? Let's say you start at the North Pole. You walk from the North Pole to the equator. You turn east. You go east for a long time, quarter of the way around the Earth. You then turn north.
No.
You come back to the North Pole, and what angle do you make? A right angle.
I don't like What's the issue, Micah?
Triangle with 3 right angles.
I have a problem.
You live on the Earth, but you can, but Mars is like that too.
Everywhere you go, Micah, it will be like this.
Unless you find a beautiful planet.
Well, like, isn't the problem with that the fact that the lines are just...
So that says the problem is that it's because it's not a flat surface, right? Okay, so based on this, we can see that
Listen, don't try to bring pointers.
that space-time behaves, I only say behaves, as though it were curved.
Oh no.
Okay?
Oh,
That's
the
mathematically what Einstein comes up with. It comes up to be identical. Mathematically, space-time behaves as though it is curved in another dimension. So this is a 2-dimensional surface, what we, the ground, curved in the 3rd dimension, right? Space-time behaves like a 4-dimensional surface curved in another dimension. You can't visualize that, but you can make analogies to it, right? Okay, so space-time behaves as though it is curved. That's what we can conclude from this. Einstein came up with this substantially later. It's kind of fun. The actual work was all much more mathematical. Okay, he went the other way. He did the hard stuff first, and then showed this, came up with this example. So the example does work, but that's not actually how you derive general relativity. So space-time behaves as though it were curved. And so then the question is, what makes it curved? Einstein looks at it and he finds the presence of energy causes space-time to curve.
Wait, I thought gravity did that as well.
No, I never said that.
Okay, yes.
Energy causes space-time to curve. And now, I forgot to, unfortunately, they're in the next group. I forgot to do this, but I have them right over here, I think.
Is it
So,
fluid?
Doesn't that mean more mental and math?
Come back.
Energy to curve.
I'm not thinking because gravity bends both space and time, so therefore, I'm not insane, right? I didn't make any sense.
You're asking me if you're insane? The person who hasn't slept for
Benji,
4 days?
am I correct?
Yes, gravity does bend space and time.
Thank you.
That's how wormholes work. Gravity, intense gravity bends space and time, causing it to actually puncture itself and create interdimensional traffic.
I never said that.
Like gravity is dependent on mass,
Not
right?
the same. No.
If gravity is dependent on mass,
Mass is a form
mass is a
of-
form of energy. Is gravity a form of energy?
No. What?
Okay, wait, let's think about this for a second.
This is actually really interesting. Depended on energy, surely.
Yeah, sorry, listen, you have to use your imagination.
Yes.
I want you to imagine, here's the standard one.
Aren't we all
Kinda
just
like
a
my
3-dimensional scan on
Imagine a mattress.
A what?
Okay. Imagine, like, say it's a really perfect one, a stiff one, but not too stiff. It's still bouncy. Well, like, I mean, it's not too bouncy, like a water bed or something, right? Okay. So let's imagine, or a sheet of latex is what other people say, but most people don't have a lot of experience with sheets of latex, you know? So, mattress. Let's say you take a small marble, that's the part I couldn't find. I couldn't find any small marbles. And roll it across the mattress. It will go like this. Good. Now, let's take the mattress and you put a bowling ball in the center of it. The bowling ball, of course, as you know, sinks into the mattress. As it sinks into the mattress, it curves the mattress around it. right? Now, when you roll the ball across, what happens? When you have a big spot here, the ball, of course, will curve towards that spot in the center. What does this look like? It looks as though this thing is being attracted by the ball in the center.
It looks like it's being pulled by gravity.
It's almost as if it's being pulled by some kind of force, right? So Einstein argues that particles move in straight lines in curved space-time. Straight lines, but the space is curved.
I had a question.
Now, this Mattress example has plenty of limitations, but it gives you a basic idea. The space itself curves, that affects what a straight line means, right? Do you know how to do a straight line on the Earth? Do you know how planes fly? You know, if you're flying from here to Taiwan, I just did that this summer. Do you know which way you fly? Do you fly due west? You don't. It's too high. It's too long. Which way do you go? You go up over the Arctic Circle. Why is that? Well, that's called the Great Circle. If you actually look, it's shorter to go over the top than to go due west. Okay, we're used to seeing flat map projections, but the real world is the ball, and it's actually shorter to go this way than it is to go that way. Okay, that shortest distance is called a geodesic. It's the shortest distance between 2 points on a curved surface. Okay, basically, what we say is that particles follow geodesics, but they're on curved surfaces. So the way they move in curved surfaces. So when you have the presence of a lot of energy in the form of mass, like a planet, it curves the area of the space-time around it, and that curvature causes the geodesic to change its shape. Thank you.
So is gravity a form of energy?
No. According to Einstein's formulation, gravity is not a force at all, nor is it a thing. Gravity, what we call gravity, is just a property of space-time. Okay? When there is any energy somewhere, it causes space-time to curve. When space-time curves, it causes the paths of particles to change. When the paths of particles change, what we see is as though a force, an invisible force, is pulling them together. Right? But what is actually happening, what the theory says, is space-time is curving, the particle is still moving straight, but the space is curved. John?
Doesn't that mean that you collected a lot of energy that look like photons, per se, because they have no mass in one place? Like if you just stuffed a zillion billion photons in one space, they could.
You mean like the sun?
No, but like the sun has actual mass.
Yeah, that's too. It's true.
But
it's also got lots of
a bunch of photons from one place.
And it would distort the skin.
It would have gravity.
Yeah, absolutely.
It's weird.
Yeah.
What if you had so much mass or energy?
What an interesting question.
Hey
guys, I have limited time, so let me talk for a little bit. I know your questions, but I want to cover a few more cool things. Okay. What are the testable consequences of this? One of them is, and the first one that was tested, is if you have the Earth here, and a big galaxy here, and then a star here. Can you see the star?
Yes.
No, the galaxy's in the way.
No.
Because the galaxy's in between, right?
The star's light bent around the thing.
So, but if this is a galaxy, so it's very heavy, right? And so you can have the star's light going this way will get bent by the distortion in the space-time, which will cause it to bend this way, and you'll be able to see it on the Earth. From the Earth's point of view, it would look like it's over here. And in fact, it would actually also work on the other side. So you would see a double image. Actually, wait a minute, real galaxies are circles. So you can see a quadruple image, and if you get it lined up just right, you get actually a continuous ring of light that's called an Einstein ring. We've never actually observed a full Einstein ring. We've gotten 3/4 Einstein rings. It has to be lined up very, very perfectly for it to work. Okay? This effect is called gravitational lensing, and we use it all the time in astrophysics now. We You do a lot of work with gravitational lensing. Because it tells you, you can use the light of the stars to figure out where the mass is. Where the energy is, but let's face it, mass energy is a very highly condensed form of energy. So the mass is, like, you can figure out, when if you see light bending like this, then you can figure out there's mass here. So what if you see this effect, but then you don't see anything here? Well, that means there's something there anyway, right? And we do that sort of thing to figure out where the mass that we can't see is. We have a lot of it, it turns out. What else happens? Well, notice how I said space-time curves? I think we figured out how space curves. What does it mean how the time curves? Well, really, curvature is just something that affects your measurement units. That's really what it comes down to, right? So time curving, it just means a change in your measurement units. So what that means is that if you are near a gravitational source, let's say you're near a large chunk of energy, a large mass, then it will affect the units of your time. That is to say, gravitational time dilation. That's to say, your feet are slightly younger than your head. Explains everything. And so, right, because the closer you are to the closer you are to the gravitational field, the more time dilation you experience.
Does that mean that the mass at the center of the Earth is younger than the mass at the average of the Earth?
Yep. I'm not sure what young means for atoms, but yes. Okay, hang on. The most fun one, of course, is this hypothetical question. Actually, here's the thing. Einstein's field equations here, I'll write them for you. These are Einstein's field equations. This is the mathematical theory of general relativity. It looks like this. There you go. That's the what's between the A and the T? That's a pi, sorry. E pi. This is in particle physics units where C equals 1 and also G equals 1, and you use gravitational constants also equal to 1.
Does that say NV?
That's a mu nu. G mu nu equals 8 pi T mu nu.
What is that?
Mu is a Greek letter and nu is a Greek letter.
Wow. That explains so much.
So this is the theory of general relativity. What are these things? They're rank 2 tensors. They're anti-symmetric rank 2 tensors. Symmetric rank 2 tensors. Of 4 dimensions, so they're 4 by 4 tensors, and that means that this is actually, but each of these are actually, if you actually expand what they are differentials. Let's say they're a bunch of derivatives. And so this is a series of differential equations. 10 linked, nonlinear differential equations in 10 variables. Einstein came up with that, and he's like, wow, I'm pretty sure this is impossible. The next year, the first solution was found. There's different equations always in multiple solutions. The first one was found that next year by a man named Schwarzschild, which is an awesome name. Schwarzschild. And so Schwarzschild found the first solution, which is the simplest one, a spherically symmetric case, where everything is spherically symmetric. The mass simplifies a lot, and he is able to find a closed form mathematical solution. Since then, computers have found thousands of possible solutions. But he found the first one, and he did it by hand, and that was cool. And it's spherically symmetric. And when he did that solution, he found something really interesting. Okay, for normal behaviors of like a ball, it has to be spherically symmetric, right? That's okay. Planets are spherically symmetric, so we're cool. So if that's normal behavior, you get things moving like you think do. In fact, you can even show that if the mass isn't that large, it acts just like Newtonian gravity. That's cool. So it shows like, wow, it's actually the same gravitation going on, right? So that was exciting. But then he found something else that was really quite interesting. And that is, if you make this thing small enough, let's say you take, say, the Earth or whatever, the sun. Okay, actually, you take the sun, and then you squeeze it down so that it's smaller than the Earth. Okay? So there's a certain mass to radius ratio that you have to be concerned with. And if you get smaller than what is called the Schwarzschild radius,
black hole.
if you reach the Schwarzschild radius, then you actually cause your equations to divide by 0. Just at one point, right in the center. Right in the center, if you pass this point, your equation starts to divide by 0. And you're like, is that okay? Well,
no.
I mean, no. Well, like maybe if you can do it at just one point. So when you do it at just one point, it has behavior basically of 1 over r. Very, very roughly, of 1 over r, right? Meaning that if at r equals 0, there's what's called a singularity. So called because because it happens at only one spot. It's infinite, but only at one spot. So the integral is still finite.
And then everything goes.
So, if you have a singularity, that is a point where the space-time curvature becomes infinite. Right? Because it diverges, right? With 1 over x. So, what does that mean? Well, according to predictions, within a certain region, which is given by the Schwarzschild radius, okay? Within that certain region, then the curvature is so great that all geodesics curve back. Okay? What people say is, oh, not even light can escape. No, it's not about gravity, it's about curvature. The curvature is so great that you can't curve enough. Or you curve too much, I should say. So that no matter which direction you go, it ends up going towards the center, because it's curving so much. That's to say, if you stand inside what's called the event horizon, the edge of this Schwarzschild radius is called the event horizon. If you stand inside it, every direction you look goes to the center.
So if you like spin around in a circle and that
You can't go around a circle. No matter where you go to the center.
So you can point in any direction,
Every
like
direction
this,
you point
and it will be
to the
pointing
center.
to the
It's like
center.
a singularity. And you're like,
Shouldn't
what?
work.
So hang on, I don't have time. So therefore, because of that, anything trying to get out will fail, including light, which means, what color will this thing be?
Black.
Black. And what will it be?
A hole.
A hole. Good. And this would be called a black hole.
How creative, maybe.
Black holes were not discovered for another 40 years after they were first postulated. But those people thought they were theoretically possible. Just because they're theoretically possible doesn't mean they actually exist, right? It's theoretically possible that we have a human, but we don't have any. You know?
Yeah.
We have a 9 foot, 8 foot 11. But so yes, that's what. Now, an interesting thing about the black hole, a fun little thing. The equations work exactly the same way if you just reverse the sign on everything. Meaning it's also theoretically possible to have a white hole.
Yes.
A white hole is a region of space where nothing can stay inside of it. All points, all directions lead out.
Wait.
Yes.
Wait, what if a white hole and a black hole interact?
Wait.
What?
What if you have just
You can't do that.
It's theorized that a black hole goes into a white hole.
perfectly
No.
flat.
It bends space and time so much that the white hole's in the past and the black hole's in the future. So it's the same
If you take
thing.
a black hole and connect it to a white hole,
It's one through.
you get a wormhole.
Yeah.
Yeah.
Through space and time.
Anyway, you might then go.
I have too many questions.
Yeah. Like what if you curve space? What happens?